Pile foundations are an essential part of building sturdy structures, especially when dealing with weak or unstable soil conditions. Imagine them as long, slender columns driven deep into the ground to transfer the weight of a building to stronger, more stable soil or rock layers below. This transfer of weight ensures the stability and safety of the structure. Pile foundations are not a new invention. They have been used for centuries. Ancient civilizations utilized wood piles to construct buildings in areas with soft or wet ground. Over time, with advancements in engineering and materials, pile foundations have evolved to incorporate various materials and construction techniques. Why are pile foundations necessary, you might ask? The answer lies in the nature of soil and its ability to support loads. In some instances, the surface layers of soil might be too soft, loose, or compressible to bear the weight of a heavy structure. Constructing a building directly on such weak soil could lead to excessive settlement, which can cause structural damage, cracks, and even collapse. Pile foundations overcome this challenge by bypassing the weak soil and transferring the load to deeper, more competent strata. Pile foundations can be classified based on various factors, each influencing their suitability for specific ground conditions and project requirements. One way to categorize them is by their load transfer mechanism: end-bearing piles, friction piles, or a combination of both. End-bearing piles, as their name suggests, primarily transfer the load to a strong stratum, such as rock or dense sand, located at the bottom of the pile. Friction piles, on the other hand, rely on the frictional resistance between the pile surface and the surrounding soil to transfer the load. Another classification method is based on the material used for construction. Common materials include concrete, steel, and timber. The choice of material depends on factors like load carrying capacity, durability, and environmental conditions. Understanding how pile foundations transfer loads is crucial in selecting the appropriate pile type for a specific project. As mentioned earlier, the two primary mechanisms are end-bearing and friction. In end-bearing piles, the load is primarily transferred through the tip of the pile to the strong underlying stratum. This mechanism is particularly effective when a hard stratum, like bedrock, is relatively shallow and can be reached economically. Friction piles, conversely, depend on the frictional resistance developed between the surface of the pile and the surrounding soil. The load is transferred gradually along the length of the pile as it interacts with the soil. Section 5. Delving into concrete piles. Concrete piles are a popular choice for pile foundations due to their high load carrying capacity, durability, and resistance to decay and corrosion. They are broadly classified into two main types: precast concrete piles and cast in situ concrete piles. Precast concrete piles are manufactured in a controlled factory environment and transported to the construction site. They are typically square or octagonal in shape and reinforced with steel bars to enhance their strength and bending resistance. Cast in situ concrete piles, as the name suggests, are constructed on site by drilling or driving a casing into the ground and then filling it with concrete. This method offers flexibility in pile length and diameter, making it adaptable to varying soil conditions. Section 6. Precast concrete piles, construction and advantages. The construction of precast concrete piles involves several steps. First, the piles are manufactured in a factory using high-quality concrete and steel reinforcement. They are then cured to achieve the desired strength before being transported to the construction site. At the site, the piles are driven into the ground using specialized equipment like pile drivers. These machines lift and drop a heavy weight onto the pile head, forcing it vertically into the ground. Precast concrete piles offer several advantages, including high-quality control due to factory production, rapid installation, and the ability to inspect the piles before installation. However, they require careful transportation and handling to avoid damage. Cast in situ concrete piles are constructed directly at the construction site, offering flexibility and adaptability to specific ground conditions. Several methods are employed, each with its advantages and limitations. One common method is the driven cast in situ pile, where a steel casing is driven into the ground to create a void. Once the casing reaches the desired depth, concrete is poured inside and the casing is gradually withdrawn or left in place. Another method is the bored cast in situ pile, where a borehole is drilled to the required depth and concrete is poured into the excavated hole. This method is suitable for sites with limited headroom or vibration-sensitive surroundings. Section 8. Exploring specific pile types, Raymond and MacArthur piles. In this section, we delve into the unique characteristics and applications of these two specialized pile types, which have been engineered to meet specific construction needs and ground conditions. Within the realm of cast-in-situ concrete piles, several specialized types have been developed to address specific ground conditions or construction challenges. These innovations ensure that structures are built on solid and reliable foundations, even in the most challenging environments. Two notable examples are Raymond piles and MacArthur piles. These piles are particularly significant due to their unique construction methods and the specific benefits they offer in various construction scenarios. Raymond piles utilize a tapered steel shell that is driven into the ground using a mandrel, a temporary internal core. This method allows for efficient penetration into the soil, ensuring stability and strength. Once the shell reaches the desired depth, the mandrel is removed and concrete is poured inside to form the pile. This process creates a robust and durable foundation that can support significant structural loads. MacArthur piles, on the other hand, employ a double-walled steel casing that is driven into the ground. This innovative design provides additional support and stability during the construction process. The outer casing acts as a temporary support, while the inner casing forms the permanent pile shaft. This dual casing system ensures that the pile remains intact and secure throughout its installation. After reaching the desired depth, concrete is poured into the inner casing and the outer casing is retrieved. This method not only provides a strong foundation, but also allows for the reuse of the outer casing in other projects, making it a cost-effective and efficient solution in modern construction. Section 9. Construction techniques for pile foundations. In this section, we will explore the various methods and equipment used in the construction of pile foundations, which are crucial for ensuring the stability and load-bearing capacity of structures. The construction of pile foundations requires specialized equipment and techniques to ensure proper installation and load-carrying capacity. These techniques are essential for transferring the loads from the structure to the deeper, more stable soil layers. The choice of method depends on factors such as pile type, soil conditions, and site constraints. For instance, different soil types such as clay, sand, or gravel require different approaches to ensure the piles are securely installed. Pile driving, as mentioned earlier, involves using a pile driver to hammer the pile into the ground. This method is highly effective for driving piles through dense soil layers and is commonly used in many construction projects. This method is suitable for precast concrete piles and steel piles. Precast concrete piles are manufactured off-site and then driven into the ground, while steel piles offer high strength and durability. Jetting is another technique that uses high-pressure water jets to loosen the soil and facilitate pile installation. This method is particularly useful in sandy or loose soil conditions where traditional driving methods may not be effective. Drilling is commonly used for cast-in-situ piles. In this method, a hole is drilled into the ground and then concrete is poured to form the pile. This technique allows for greater flexibility in pile design and installation. Rotary drilling, auger drilling, and percussion drilling are some of the methods employed depending on the soil type and drilling depth. Each of these methods has its own advantages and is selected based on the specific requirements of the project. Vibrating techniques can also be used to install piles by creating vibrations that reduce soil resistance. This method is particularly effective in cohesive soils and helps in achieving the desired pile depth with minimal disturbance to the surrounding soil. Section 10. The importance of pile foundations in construction. Pile foundations play a crucial role in modern construction, enabling the construction of safe and stable structures in challenging ground conditions. These foundations are particularly vital when the surface soil lacks the necessary strength to support the weight of the building or structure. They are essential for various infrastructure projects, high-rise buildings, bridges, and waterfront structures. Without pile foundations, many of these structures would be impossible to build, especially in areas with soft or unstable soil. Understanding the different types of pile foundations, their load transfer mechanisms, and construction methods is paramount for engineers, architects, and construction professionals. This knowledge ensures that the right type of pile is chosen for each specific project, taking into account the unique ground conditions and load requirements. Selecting the appropriate pile type and installation technique is crucial to ensure the long-term performance and safety of the structure. Different types of piles, such as concrete, steel, and timber, each have their own advantages and are suited to different types of projects and ground conditions. By transferring loads to stronger soil or rock layers, pile foundations mitigate the risks associated with weak or unstable ground conditions, providing a solid foundation for structures that stand the test of time. This load transfer is essential in preventing settlement and ensuring the stability of the structure. Their importance in ensuring safe and sustainable construction cannot be overstated. Pile foundations are a key component in modern engineering, allowing us to build taller, stronger, and more resilient structures that can withstand the test of time and the forces of nature.